After a 1.5 million kilometer journey, the James Webb Space Telescope has arrived at the Sun-Earth L2 point. It did this by executing its final mid-course correction burn called MCC2. It lasted just 297 seconds, or a little less than 5 minutes, and it only changed Webb's speed by about 1.5 meters per second. That's a brisk walking pace. It may not seem like much, but it was enough to place Webb into an orbit around L2. In fact, it placed it into a very large orbit, one that's more than twice as large as the Moon's orbit around Earth. It'll take Webb about 6 months to complete a single orbit around L2, and this first go-around is jam-packed with mirror alignments, phasing, instrument calibrations, moving target tracking tests, verifications, station-keeping maneuvers, and finally, the first science observations. But what exactly is so special about L2? I mean, it's just a point in space, and it's an empty point in space at that, so how can Webb orbit something that isn't there? Well, it is true that L2 is empty, but orbiting empty points in space is actually very common. And that's because whenever there are two massive bodies that are orbiting each other, they both orbit a common center of mass, or barycenter. If the objects are massive enough, the center of mass lies somewhere in between. We only say that the Moon orbits Earth because its center of mass is located inside Earth. But Pluto and Charon have similar masses, so their barycenter is somewhere in the space between them. So the fact that something can orbit an empty point in space really isn't all that unusual. But at the same time, that's a two-body system. It doesn't explain how Webb can orbit a point that's outside of another two-body system. Well, the good news is that we can break this problem down and understand just what the L2 point is and how Webb can orbit around it. In fact, there are many spacecraft that have orbited L2, such as NASA's WMAP satellite and ESA's Planck and Herschel telescopes, and Russia's Spectre RG and ESA's Gaia spacecraft are both orbiting there today. In fact, Gaia is featured in an episode of Space: The New Frontier, which is a series on Magellan TV, who I'd like to thank for sponsoring today's video. With more than 3,000 documentaries on nature, history, space, science, and technology, Magellan TV always has something amazing to watch. New documentaries are added each week and are presented without commercial interruption. And now, Magellan is offering my viewers a full month of their award-winning content absolutely free. Just use the link in the description of this video. L2 is one of the 5 Lagrangian points between the Sun and Earth. Actually, these 5 points exist around any two-body system. So there are Lagrangian points for the Earth-Moon system, a set of points for the Sun-Jupiter system, and so on. Now, if a third object is placed at any of these points, the gravitational forces of the two large bodies combine in such a way that holds the third object stable with respect to the others. The practical upshot is that as the system orbits, the third body tags along. And that's why the Sun-Earth L1 point is a great place to position sun-facing missions like the Solar Heliospheric Observatory and Earth-facing missions like Discover. Likewise, L2 is the place to put astrophysics missions like Gaia and Webb. At both locations, spacecraft maintain a constant line-of-sight communication with Earth even as Earth orbits the Sun. But L2 is particularly important for Webb because it can block the heat of the Sun, Earth, and Moon with a single sun shield. That's a perfect place for infrared astronomy. But there are some important caveats. For one thing, the third object has to have a mass that's really small relative to the larger bodies. Now, obviously, that's not a problem. Webb's mass is negligible compared to Earth, let alone the Sun. But the other caveat is that the Lagrangian points are at best described as metastable, especially the first 3 points. To understand what I mean, imagine a saddle that's perfectly smooth and frictionless. Now imagine trying to balance a marble in the very center of the saddle. It's theoretically possible, but as a practical matter, it's extremely hard to do. The L2 point is a lot like this. An object moving perpendicular to the Sun-Earth line falls toward the center, but then it either falls toward or away from Earth. Now, if Webb falls away from Earth, it's really in trouble because the only way to bring it back would be to turn it around and thrust back. But that would cause the telescope to suddenly warm up, all of the structures would expand, glues and adhesives would melt, and the mission would be over. And that's bad. Webb has thrusters only on the warm, sun-facing side of the observatory. And that's because hot thrusters would contaminate the cold telescope side with heat or with rocket exhaust that would otherwise condense on the optics. And that would also be bad. A safer approach is to place Webb almost, but not quite at L2. And that way, when it falls back toward Earth, a tiny thruster burn pushes it back almost, but not quite, back to L2. And this means Webb never runs the risk of actually falling beyond L2 where it cannot be recovered. And that's why the Ariane 5 launch was intentionally designed to slightly undershoot and let the spacecraft do a series of mid-course correction burns. The first two, MCC-1A and MCC-1B, were executed on the way out to L2. However, arriving even just shy of L2 leaves us with another problem. At that distance, the Sun is in a permanent annular eclipse by Earth. Webb is solar-powered. Now, it could use nuclear power, but that's expensive and hard to do. Another complication is that Coriolis forces would cause Webb to librate around L2. In other words, Webb would find itself in a tiny orbit around L2 that would need even more thruster burns to manage. Oh, and the moon's gravity on Webb is also still a thing, and it's constantly varying as it orbits Earth. It turns out that these real-world complications can be addressed by simply taking up a large orbit around L2. But how is it possible to orbit something that isn't there? I mean, L2 is still an empty point in space. Well, to help us understand better, let's look at the problem by considering some of the forces acting on Webb. If Webb were actually at L2, it would be feeling gravitational forces from the Sun and from Earth. So let's draw them separately so that we can keep track of them. Now, Webb is orbiting the Sun at the same time, so we can also imagine a centrifugal force pulling Webb in the opposite direction. Now, the great thing about L2 is that at this distance, the centrifugal force is exactly balanced by the gravity of the Earth and Sun. Now, you may have heard that there's no such thing as a centrifugal force, and that is correct. But we are talking about a rotating, non-inertial frame here, so centrifugal forces are still a useful way of summarizing all of the real effects that are going on. Oh, and we're not going to worry about the gravitational effects of the moon or even the fact that the Sun and the Earth are not point sources. We're just going to keep everything simple for the time being. Now, let's move Webb up some distance away from L2. Now, the gravitational force from the Sun changes a tiny amount, but not very much because it's over 150 million kilometers away. But Earth is just 1% of that distance, so its gravity changes considerably. Because Webb is now farther away from Earth, its gravitational pull gets weaker. It's also no longer parallel with the Sun's direction either. So let's break it up into its x and y components. Now we can really see the problem. The centrifugal force is in the x direction of our diagram, but it's actually greater than the gravitational forces from the Sun and Earth. That means Webb is going to drift both down and farther away from L2. So we need to fix this drift in both the x and y directions. First, we bring Webb a little closer to Earth so that it's now hovering above a new point that we'll just call L2 prime. Earth's gravity gets stronger, and its x component helps to balance the centrifugal force once again. But the y component has gotten stronger as well, so Webb wants to move downward. But the closer it gets to the Sun-Earth line, the stronger Earth's gravity gets and the more it moves toward Earth. We can't let that happen either, because then the heat load would become too strong for the sun shield to handle. However, we can counteract this downward force by giving Webb a sideways push into the screen. This sets up a new centrifugal force that balances the downward force of Earth's gravity. When combined with the sideways motion, Webb takes up a new circular halo orbit around L2 prime. And that means there doesn't have to be a physical mass at L2 prime in order to attract Webb. Rather, Webb is simply being pulled by the y component of Earth's gravitational force. Now, this is an oversimplified discussion of Webb's orbit around L2. We deliberately ignored real-world complications in order to understand how Webb can orbit something that isn't there. But getting into Webb's actual orbit required taking all of these real-world complications into account. So, to make things easier, Webb wasn't actually launched to L2. Instead, it was launched to a point along the side of L2. As it was starting to fall away, Webb executed its MCC-2 burn to settle into its orbit. Since part of this initial fall was directed in the X direction toward Earth, the burn propelled Webb into an orbit that's now tilted by about 33 degrees. The orbit isn't perfectly circular either, but rather follows an elliptical shape. As a result, Webb's distance from the L2 point varies between 250,000 kilometers and 832,000 kilometers. Now, for reference, the Moon's semi-major axis is about 400,000 kilometers. So Webb's orbit around L2 is enormous. This large orbit was chosen because it makes getting to L2 a lot easier. The farther something is from its orbital focus, the slower it moves and the less energy is required to maneuver. And that's why it only took a 5-minute burn and a 1.5 meter per second delta V. The large orbit also means that Webb will never drift into the shadows of the Earth or the Moon during its mission. However, larger orbits can permit stray light from the Earth or Moon to get past the sun shield and reach the primary or secondary mirrors. In addition, a larger orbit can reduce the number of communication opportunities with the deep space network. That's why Webb will have to change its orientation to keep stray light off the mirrors at all times throughout its orbit and schedule the communication downlinks accordingly. The Webb takes about 6 months to complete one orbit around L2. Although it sometimes flies out just a little bit past this point, the geometric center of the orbit is still centered on the L2 prime point on the Earth side. Remember, we don't want that ball right at the very middle of the saddle. That's why Webb will execute small station-keeping burns every now and then to maintain its orbit. Missions like Gaia only require 3 to 4 of these burns every year. But Webb will require much more frequent burns for a couple of reasons. For one, its sun shield is always feeling a torque from solar radiation pressure. Webb can counter this rotational force by spinning up its reaction wheels, but the solar radiation pressure is unrelenting, so the reaction wheels must increase their spin over time. Eventually, a station-keeping burn is required to rotate Webb back into place and let the wheels throttle back. Webb also changes its orientation as it points from one position to the other. All of these motions perturb Webb's orbit ever so slightly, requiring more station-keeping burns to maintain. And that's why Webb executes a burn once every 21 days. The exact timing and duration of those burns are calculated by the flight dynamics team at NASA's Goddard Space Flight Center. They'll do this by monitoring Webb's telemetry data and using ranging data from the Deep Space Network to pinpoint Webb's location and its motion at all times. They even take into account gravitational perturbations from the Moon and even the gravitational perturbations of the rest of the planets. So yeah, the flight dynamics team are really awesome, and they've got their work cut out for them over the next 20 years. And speaking of amazing teams, how about these amazing folks who are helping to keep Launchpad Astronomy going? And I'd like to welcome Marcel Barros, Steve C., Joe Curley, Timothy Fudge, Chris Gregory, Eric Johnson, Navanitha Krishna, Barry Stott, and Lucy Thursfield as my newest patrons. And if you'd like to join me on this journey through this amazing universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.